Alright, this video we're going to be looking at logic gates. Now a logic gate is a logical function that takes one or more inputs and produces a single logical output. Alright, and by logical we're talking about 0 or 1. Alright, we're back in binary again. A logic operation can be also known, okay, so logic operation is another name, or Boolean function. And we're going to be looking at Boolean operations in the next series of videos. So let's have a look at what a few logic gates look like. The simplest of all logic gates is the NOT gate. And being a logic operation, we have an input, let's call it A, and an output Q. And we can draw a truth table for this associated gate. Now, remembering the rule from the truth tables video, number of inputs, so 2 to the power of 1 equals 2 rows in our truth table. 0 and 1, A and Q. And a NOT gate basically states that if A is equal to 0, then Q is equal to not A, or in this case equal to 1. So it is simply the opposite. A NOT gate inverts its input. And the easiest way to remember that is this little bubble. Wherever you see a bubble, as it's known, that is a NOT / invert operation. Right, so NOT gate is purely used for inverting a signal. Okay, if this was 5 volts coming in here, that would be 0 volts coming out here. 0 volts coming in here would be 5 volts, or whatever the voltage level is coming out again. So that's the simplest gate and performs a very simple operation. And that could be written as Q equals not A, or A with a bar over it. And we're going to get onto these shortly when we have a look at the Boolean expressions. But just for now, these are the Boolean expressions related to them. Alright, the next one is the AND gate. And it's important that you actually remember how to draw these symbols. Okay, an AND gate has this straight bit here and then a rounded semicircle here. 2 inputs, 1 output, so our truth table will have 4 rows, and it will also have that extra input column. We can do it by counting in binary, or we could use Martin's rule to fill it in. In this case, an AND gate, if A and B, hence its name, then the output is on. Otherwise it's off. If A and B, then the output is on. Otherwise A and not B, nope, it's not going to happen. And so this is written as Q equals A and B. Alright, so the multiplication or a dot here in Boolean means it is an AND operation. Next one we have is the OR gate. Also having 2 inputs and 1 output. A, B, and Q. Our truth table will also have 4 rows. 0, 0, 0, 1, 1, 0, 1, 1. Our output, an OR gate says if A or B, So A or B? No. A or B? Yes. A or B? Yes. A or B? Yes. Right, so if either A or B is high, then the output is high. And in Boolean, it is written as A plus B, where plus is the OR operator, multiply is the AND operator. Alright, and the last fundamental gate is the XOR, which is drawn like this. Also having two inputs, but it has a slightly more complicated truth table. Not overly, but slightly more complicated. A, B, and Q, 0, 0, 0, 1, 1, 0, 1, 1. Right, and what the XOR says, this X stands for exclusive. Exclusively OR. Alright, so if A or B, but not both, that's the exclusive part. So 0, A or B, but not both, A or B, but not both. Here's the both, so that one comes to 0. So just watch out. That's the row that changes between the XOR and the OR gate. Right, and that uses a special symbol, a plus inside a circle, to represent the exclusive OR operation. So those are our fundamental gates, the NOT, the AND, the OR, and the XOR. Right, you need to remember these symbols, you need to remember the truth tables associated with them. Right, thankfully the names should help you remember their functionality. A or B, A and B, not A, alright, and A exclusively OR B. There are other variations to these, which are basically the same gate with a NOT gate built in. So this is the same as, for example, drawing that, except the little arrow is dropped just to make it a little bit more convenient to draw. So these are equivalent. And this is what's known as an AND or NOT AND. And the easiest way I find to remember the truth table for these ones is when you go to fill out the truth table, A, B, I'm going to do, so this will be Q, and this will be not Q. 0, 0, 0, 1, 1, 0, 1, 1. Okay, work out what it would be here. So this would be the not Q before it is then inverted. Okay, so if it was an AND gate, this would be the functionality. Alright, through here it goes through a NOT. So this then becomes the inverse of it. So once again, if you've got a NAND gate, okay, everything excluding, so the first three columns here is the truth table for it, but it's often easier if you can remember the NAND and AND gate. So this would be a normal AND, that would be the behavior. If you invert each of these, you'll get to the operation of a NAND gate. And in Boolean algebra, A and B not. Alright, so you do the A and B and then you invert it. And similarly, we have the NOR gate, which is the same with an inverting output there, A, B, Q. Okay, and you might like to have that extra column to help you remember it as I do. A, B, Q. This would be if it was an OR gate. 0, 0, 0, 1, 1, 0, 1, 1. So if it was an OR gate, 0, 1, 1, 1. Being a NOR gate, it is 1, 0, 0, 0. Okay, just the opposite of a normal OR gate because of that inverting output. Alright, and so we get Q equals A or B, not. And that's what that bar above means. Right, probably should have highlighted that. Okay, so the bar up here means to invert. Now, as well as having single gates, as you see here, there's nothing stopping you cascading gates together to form what's known as a logic circuit. Alright, so if I wanted a 3-input AND gate, I could take 2 AND gates and cascade them together, or what would more practically be done is just to draw an AND gate with 3 inputs. So this is a 3-input AND. A, B, C, A, B, C. Both are equivalent. Alright, A and B, you can work out the truth table for this, then work out the truth table for that, or chuck it all into one big truth table with the corresponding correct number of rows and columns, as it seems. C, Q, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Noting we have 8 rows because we have now 3 inputs, 2 to the power of 3, and only if all 3 are on, A and B and C, then the output goes to a 1. Otherwise, it would always be 0. Alright, so remembering logic gates, a logical function takes one or more inputs and produces a single logical output. You know, all of these only have one output. Alright, logical being 0 or 1, we're working with binary, and hence our inputs are always described using binary. Each gate has a truth table associated with it. Remember the symbol, remember that little bubble, remember what this bar means, and use the word to help you. The only tricky one is the XOR, the rest should be fairly simple for you.